So let's talk about a few things. Primarily, let's start out with diving toning. It's an eyedropper in a bottle full of water. I call it diving toning because Frosted Flakes had one of the free giveaways in one of their boxes, which they call diving toning, which basically serves the same purpose. Fortunately, diving toning had a little bit of a leak, so after a couple of tries, diving toning stayed at the bottom. Eyedropper works a little bit better. But I'm hoping that you can see that there is an eyedropper in there, or if your vision is not quite there, you can see that there is something in there.
When I walked past it, I thought that, I seen something, but I'm like, oh, that must be, seeing the cipher.
Alright, see that there's an eyedropper in there. So, what I'm gonna do is make the thing magically go down to the bottom, using magic and physics. Alright. Now, with the proper sleight of hand, you can actually probably pull this off quite well with a younger crowd. But stop.
Whatever, mister.
So the question is, that worked better than usual. Usually,
Can I take that home for the kids tonight? They gonna think I'm so cool, mister.
sure. Oh, so the big question is, how is that happening? What am I doing to make it go down besides psychic powers?
Are you squeezing the bottle?
I am. All right, so why does squeezing the bottle cause the eyedropper to go down?
Putting pressure on it.
Okay, what does that have to do with the eyedropper?
The pressure
Well,
from the
it's-
bottom.
When you push it, the water goes inside of the.
You don't know if that happens? Are you
Well, I'm
guessing?
saying because you push it, wouldn't it go inside of the dropper, and so that's what makes it go down?
Does it?
So I was thinking because the pressure from the bottom of it caused a little bit of pressure from the top, or loosened up the pressure from the top. I don't know.
So, wait, let's drop back for a second. First off, Erica, yes, water does go up into it. I have enough water in here so I don't have to apply much pressure. If there's a little bit more of an air gap up there, then it takes more effort on my part, and you can see my hand straining as I do it, and you can definitely see the water move up into it. I just happen to have enough water in there so that just slight pressure from my thumb will make it fall.
Cause I had to pay attention when you was over there, like, how do you see it move?
All right, so, and you said pressure at the bottom causes pressure at the top?
No, well, I was thinking it relieves some of the pressure at the top. I guess because of the movement of it. I was just thinking about the movement of the bottle and, but, go ahead, I listen.
No, I don't want to stop you if you were.
Oh, yes, that's what I was just thinking, it was just the movement of the bottom, putting less pressure on the top, or relieving some of the water that was on top.
Sort of the opposite actually happens.
Okay.
Is water compressible at all?
All right, so that's one question right there that we need to address. Water is, for the most part, incompressible. Solids and water, whatever volume you have, it's very difficult to actually change the volume of a liquid, for example. It is possible with the right equipment, but for the most part, we can consider liquids in general to be incompressible. And I put it in quotation marks just because, yes, you can compress it, but it's not easy. Well, I'm not compressing the water here, or at least not noticeably. All right, so what effect does that have, Jancy? Why does it being incompressible make any difference?
Is there air inside of the whatever's called, the eyedropper.
The eyedropper? Is there air inside the eyedropper?
Looks like there is, it's kind of hard to see.
Yeah, this, I drained water from this one and put it into the other one, so this one would be very difficult. Well, actually, wouldn't be difficult because it's right there on the bottom. Anyway, the eyedropper's pretty much set up. I don't know if that's easier to see.
Yeah, there's definitely some air in it.
Yeah, there's definitely some air in the eyedropper. All right, so what does that have to do with the water being incompressible?
Well, when you're squeezing it, if the water is not compressing, the air has to be, right?
True, and so that's another principle there.
What chapter is this?
This is the 11 through 14 group. I think officially this is 14. Well, we're gonna be hitting various aspects from chapters 12 through 14. Liquids is 13, gases are 14, solids are 12. I guess they're on, what quotation marks are on that one. Okay, so what were you saying? That you said gases aren't compressible, therefore, what does that have to do with the eyedropper falling?
Oh, I don't know, it's not like compressing the air makes the eyedropper way more. I'm still stumped.
All right, well, we got a lot of pieces in place.
If there's more, if the air is being compressed and water is getting into the eyedropper, does that cause it to drop then? Because it's, because the air is what is causing it to come to the top.
All right, well, let's see if we can actually see that. Did that seem to work?
It's almost like the air is bobbing
Mhm.
in the eyedropper.
Well, let's see. And that could just be my hand is shaking. Is water going, are you getting more water in the eyedropper?
It is, no, it doesn't appear so. Or if there is, then it's a very small amount.
Side view. So you can see where the level of the water is, the water and the air meet, right? As I squeeze, does it? Are you seeing it
Yeah.
bob up and down?
Yeah.
All right, so not touching it, as I touch it, a little bit more does go in. So why does the water go in?
Cause you're adding pressure,
Well, I'm adding pressure at the bottom,
but the whole thing is full of water.
therefore,
That pressure's got nowhere to go.
say it again,
That pressure, I don't know how, I don't know how,
give
I
it your
don't
best
know how to
shot.
word it, I guess.
I think.
I just didn't actually hear what you said.
Oh, the pressure has nowhere else to go, cause it's, I don't know, cause it's capped off inside the bottle, so it's, I don't know. how to see.
All right, I think the spirit of what you're saying is right, but yeah, let's work on the wording next.
I was about to say, I felt like he was saying it like, just like the air, that little bit of air that was in there is kinda like going into it to make it come.
That I think it's, when you squeeze it, it's forcing the incompressible liquid into the compressible gas, which is adding the more weight to the dropper, which is making it drop, and then when you let go, the gas, I guess, compresses or decompresses again, and there's less water, so it's less weight, and the air is buoyant, and,
Okay, and that pretty much,
yeah.
much better summary.
Okay.
It's not that the pressure has nowhere to go, it's that the water has nowhere to go.
Water has, that's, okay.
And it goes into the dropper.
Yes,
And it compresses the air, which is in the dropper, into the top of the dropper.
absolutely. Now, one of the reasons why if you don't fill it all the way to the top, that there's a little bit of gap of air in the top of the bottle, that it becomes a lot harder because now water, when you squeeze it, the water can go into the dropper or just go into the top of the bottle. And so it becomes a lot harder to do. But there's another principle sort of connected to something Latoya said earlier, and a couple other people hit on it. If I'm squeezing at the bottom, that pressure that I'm applying at the bottom actually affects the entire liquid. It doesn't matter where I squeeze it. If I squeeze it at any point in there, all the water inside increases in pressure. So external pressure is felt throughout. And this is known as Pascal's rate. Now, the answer that was given just then, and a couple people hit on it, is the fact that the weight of the eyedropper increased. From a semantic point of view, it comes down to what do you consider the eyedroppers? The eyedropper, the glass and the rubber and what's inside it, or the glass, the rubber, excluding what's inside it? Because the weight, if you're excluding it, so it's just the glass and the rubber stopper, the weight of it didn't change one bit. So if the thing, it's at rest right now, I squeeze it, the thing falls, so therefore my velocity changed. If my velocity changed, what had to be true?
The acceleration changed.
Okay, or the fact that there is acceleration. Yes, acceleration changed from nothing to something. And if there's acceleration, what must be true?
The displacement change? No, sorry, I was.
Velocity.
Okay, velocity change, but thinking let's not just stick in chapter 3, let's go out to chapter 2, 4, and 5. If acceleration is not zero, there's physical principle that has to be true.
So if the acceleration is not zero?
If acceleration is not zero, what must be true?
Other forces are acting on it?
There's a net force acting on it, yes. F equals ma. Acceleration is not zero, the force isn't zero, total force. All right, so we have the stopper right here. What are the forces acting on it?
Weight,
Okay,
normal force on the water, or that's not present in.
there is normal force here. You're talking, I guess, from all over the place.
Force of gravity,
Wait,
I mean, not force of gravity,
Is there a force of like, with a buoyant, it's not buoyancy, but, I mean, yeah, I guess it is buoyancy, but
buoyant force.
a buoyant force, okay.
All right,
buoyant force.
which way is buoyant force acting on it?
Was it up?
Trick question,
Why?
cause you could have been squeezing a bottle. You could have been.
Buoyant force is still gonna be in the same direction.
Yeah? Okay.
And it's possible that some scientists have set up an environment where this isn't true, but I haven't done that.
Okay,
Buoyant force is an upward force,
okay.
because there's more force coming from the bottom than coming from the top. All right, so we have buoyant force up and weight acting down. Now, right now, there's one other force acting on the stopper at this very moment
Contact? Oh, no, sorry.
with,
Huh?
you said contact,
Yes.
with what is it touching?
What is what touching? The
Is it
bottle?
friction?
The stopper, what is the stopper touching?
Oh, it's touching the cap?
Yeah, so right now the cap is also pushing down on it. Now, once I squeeze it, it releases, it's no longer touching it, so that normal force goes away. So I'm going to ignore that, even though I just want to acknowledge that there is an additional force acting on it at the very beginning. So what is buoyant force equal to? Formula. I know we did it in class because you had a lab coming up.
did you ask?
I-
What did you ask?
What is the formula for buoyant force?
Oh, my God. Oh, no.
Presumably just two enthralled are rated now.
And plus, I don't have my physics lab book, so
Okay.
I'll be back there. The first thing I was supposed to be looking at chapter 13 already?
No, we had discussed it already. I was hoping somebody went back to the notes and just say what the formula was. It was a dream.
There's two
I'm
of them
gonna
on
ask you
here.
about it too.
There's the M minus M parent, I think, and then in parentheses and D, but then there's another one that uses volume.
It's gonna use volume at some point.
Where's that?
That's the one right there.
Okay, cause there was another one on the next page.
So according to that lab, buoyant force was rho, F, V, and was there a subscript next to V?
Just G, no, well, yeah, no, there wasn't.
Okay, so that,
Yeah.
all right, so this right here is, that's density times volume. This is a mass. And so ultimately, the buoyant force is a mass times an acceleration due to gravity. Now, it's not officially weight. It's derived from weight of fluid, but it's not officially weight. This is the density of the fluid. This is rho sub F, density of fluid. And V is the volume of the object. Sorry, reword that. Volume of fluid, of displaced fluid.
Volume of displaced fluid.
Yes. In other words, how much water has been pushed out of the way? So when we start out on the eyedropper, we have water all around it, but there's gas bubble inside. That gas has pushed water out of the way. So whatever the weight of the water that would have been in this space, that's the buoyant force. As you squeeze on the bottle, pressure is exerted everywhere. Pressure is exerted, that means a force. Pressure is a force divided by area. So as you squeeze on the bottle, water starts to fill in here, which means there's less, gas takes up less space. If gas takes up less space, the buoyant force drops. And I got my two forces right here. I got weight and buoyant force. So if my buoyant force gets small enough, weight becomes dominant and it will sink. So they used a lot of terminology, some of which you've heard before, some of which you might be less familiar with, so let's hit a couple of those. So let's talk about density. Or, as one dictionary, it did get corrected, Merriam-Webster dictionary once had the word "dord" in it. You want to get the story? They sit around looking for input of new words to various academics around the country, and somebody sent in, what he wrote was D or D for density, and the person who received it misread it as Dord, and it did show up in the dictionary for a few years till they corrected it. But I tend not to use D, I tend to use the letter rho. Density is mass divided by volume. Now, when we did this in class the other day and we figured out what is my volume, it's about 1/10 of a cubic meter, pure rate. I started out with the assumption that my mass, my density was about the same as water. Why would I think that my body is about the same density as water?
Cause our body is made of 70% water.
Yeah, but what about that other 30%?
Blood, other fluids.
I'm hoping there's some solid in me. I assume at least one person in here has been to a swimming pool before.
Yeah.
Is it from the air in your lungs? I don't know.
Keep going.
It balances out that 30%
Uh,
in the water. I don't know.
How do you make if you're in the water, how many of you just step in the water and just immediately sink down? How do you get to sink?
You have to hold your breath and.
Don't you have to?
I'm not talking swimming to the bottom, no, not swimming to the
Oh,
bottom.
okay.
I'm talking if I'm floating in the water, usually, if
If you breathe out.
top of my head, yeah.
Yeah.
So the difference between floating in water and sinking in water, for most of us, not everyone, but for most of us, it's I'm floating, I'm sinking. It's not a lot of difference there. So my density is roughly that. Now, some people can be a little bit denser than water, some people a little bit lighter than water. Body fat also makes a difference about how easy it is to sink or swim. So that's why my density is about that of water. My density is more than water. In other words, I can somehow reduce my volume but keep my same mass. Then the buoyant force, I'm not taking as much space, I reduce the amount of buoyant force the air or the water exerts on me, my weight becomes dominant and I sink. I think it was Hurricane Floyd, there was that hurricane in